Yeah, dual nature MCQ from, well, it is actually multiple select question on dual nature from Nest 2020 second shift question number 12. Sorry. Okay, second shift question number 12. This is a multiple select question, so we need to check each and every option's validity. Let's read the question. Thermal de Broglie wavelength is the de Broglie wavelength of the gas particles. Excuse me. Thermal de Broglie wavelength is the de Broglie wavelength of the gas particles in an ideal gas at temperature T with average kinetic energy given by the equipartition theorem and usual relation between kinetic energy and momentum. Consider an ideal monoatomic gas A of Na atoms, each of mass Ma, and another ideal monoatomic gas B of Nb atoms, each of mass Mb is equal to 4m. Both gases are uniformly distributed in boxes of volume V at temperature capital T. Select the correct statement or statements. Option A. If a photon has wavelength equal to thermal de Broglie wavelength of atoms of gas A, then the ratio of photon momentum and average momentum of atoms in gas A, that is P photon upon Pa, is 2 by 3. B. If total mass of gas A is the same as total mass of gas B, then their pressures are related as Pb equal to 4Pa. C. Thermal de Broglie wavelengths of gases A and B are in the ratio lambda A to lambda B equal to 2. If volume and temperature are such that for both gases A and B, the average interparticle spacing in each direction is equal to the thermal de Broglie wavelength of respective atoms lambda A and lambda B, then Nb is equal to 8 Na. Now look, in this question they have combined the dual nature concepts with kinetic theory of gases concepts. Okay, and they're using a term called thermal de Broglie wavelength. Okay, now what is de Broglie wavelength? We know de Broglie wavelength formula. Lambda is equal to h by p. Okay, that is the formula that de Broglie gave us. But here momentum p is to be calculated using kinetic theory. Okay, what is momentum p? Momentum p is to be calculated using kinetic theory of gases. Okay, using kinetic theory of gases. Okay, now look, let us first go for option C. Let us first see whether it is correct or incorrect. Thermal wavelengths, thermal de Broglie wavelengths of gases A and B are in the ratio lambda A by lambda B equal to 2. Okay. Now look, they're saying, so it's a monoatomic gas, which means it is going to have only 3 degrees of freedom. Okay, monoatomic gas, so 3 degrees of freedom, let's write it here. Monoatomic gas, only 3 degrees of freedom, and that too translational, no rotational or vibrational degrees of freedom. And for such gases, what formula holds for the RMS speed? This formula. Okay, this formula holds for RMS speed. Okay, we will not need it for this option, but we'll definitely need it to solve the problem. Okay. Okay, now look, can we calculate the thermal de Broglie wavelength of atoms? Okay, atoms. Yes, lambda is equal to h by p. Okay, but what is p? P is under root 2 mke. Okay, we know this formula. Okay, we have used it in one of our previous MCQs. Okay, but so I will not derive it now. So you can need to memorize it, or you need to derive it quickly, right? Kinetic energy. Now this kinetic energy is actually the average kinetic energy of the gas. Okay, average kinetic energy of the gas. Have you got this formula? That Ke, see, this is not individual wavelength anymore. Okay, this is going to be the average because they have told us that specifically. Okay, with average kinetic energy given by the equipartition theorem and usual relation between kinetic energy and momentum. So that usual relation between kinetic energy and momentum is P equal to root 2mk, and average kinetic energy given by the equipartition principle means, well, now wait, let's write it. Okay, do you remember that formula? K average, yes. What is the average kinetic energy? It is 3 by 2 kBt. Yeah, 3 by 2 kBt. Now uh, the temperature happens to be the same. Do you see that? Okay, at temperature T with average kinetic energy. Mm, yeah, okay, average and kinetic energy, temperature happens to be the, no, can you consider that? No, we can't say that, right? We cannot say that. It's just that thermal equivalent at temperature capacity. Okay, what can we then do? Hmm, okay, instead of using 3 by 2 kBt, let us use the formula half m Vrms squared. Okay, that is the average kinetic energy. But again, that temperature pops up, right? Hmm. Yes, I think we have to take temperature to be the same for both the gases. Oh yeah, okay. Look. Here they are saying both gases are uniformly distributed in boxes of volume V at temperature T. Yes, okay. So we can take temperature to be constant. Okay, fine. We can take temperature to be constant. And because kinetic energy average is directly proportional to that, okay, there is no need to write this. There is no need to write this. We can directly say that it is 3 by 2. Okay, so lambda is equal to h upon under root 2 m into kinetic energy average is 3 by 2 kBt, kb Boltzmann's constant. Yes, okay, now we got it. Therefore, lambda varies inversely with root of m. Okay, lambda varies inversely with root of m because temperature is constant, or I would say temperature is same. Temperature is same for both the gases. In fact, their volume is also same, right? That's what we concluded from the last part. Yes. Okay. Therefore, lambda a into root ma is equal to lambda b into root mb. Which ratio do they want? Lambda a by lambda b. Lambda a by lambda b is equal to root of mb by ma, and we know mb is 4 ma. Okay, look here. Mass of atom of gas B is 4 times heavier than that of A. So mv is equal to 4 ma, so mv by ma is 4, so that is 2. lambda A by lambda B is true, option C is correct. Okay, option C is correct. Okay. Okay, now let us come to option B. Okay, where they want us to find out the relation between the pressures. Okay, where they want us to find the relations between the pressures. If total mass of gas A is same as total mass of gas B, then their pressures are related as PB is equal to 4PA. So which condition applies specifically for option B? Mass of A is equal to mass of B. Okay. Now look, what is the formula for pressure? Pressure is equal to 1 by 3 rho, that is density, into VRMS squared. 1/3 rho, we say V squared bar or VRMS squared by definition. Okay. Now what is rho? Mass upon volume. Okay. So if Ma or if M represents mass of one atom, and if N represents the total number of atoms, the total mass will be Mn upon volume V into, now for that VRMS, we can use the formula here. Okay, we can use the formula here, and you need to know the formula, otherwise it will be a bit difficult to solve the question. Okay, into 3RT upon, this is the molar mass. Okay, what is M naught? Molar mass. Okay. Now let us get rid of the things that are constants. Okay, that are constants. Look, because they are saying total mass of gas B is equal to total mass of gas A, that means M into N, that's the total mass. That's same. So that is no longer a variable now. That is no longer a variable now. Okay. How about volume V? Volume V is same because that information is given in the problem, not in the option. In boxes of volume V. So both boxes have same volume, both boxes have, or both gases have same temperature. Okay. So temperature as a variable is no longer there in this equation. Okay, so it then boils down to the relation P directly proportional to 1 upon M naught. Raise your hands if you understand that. What is M naught? What is M naught? M naught is mass of one atom into Avogadro's number, because that is molar mass, right? But because Avogadro's number is a constant, P will be 1 upon M. P will be directly proportional to 1 upon M, which means PAMA is equal to PBMB. Okay, which ratio we want? Be careful now. In option C, they wanted lambda A by lambda B. Now they want PB by PA. Okay, so PB by PA will be MA by MB. MA by MB is 1 upon 4, right? MB is 4 MA. So MA by MB will be 1 upon 4. Okay. So PB is 1 upon, okay, now we need to be careful. It's PA by 4. Okay, it is PA by 4. Right? PB is equal to PA by 4. So is option B right? No, option B is not right. Okay, option B is not right because the relation that they give is PB is equal to 4PA. Instead it is PB is equal to PA by 4. Got it? You need to be a bit more careful now for solving option B part, because eventually it is, the 4 is going to appear somewhere, but it is not in the numerator, it has appeared in the denominator. Have you got B?
Yes, sir.
Yes? Okay. See, now for option B, there is no dual nature of radiation required, right? There is no dual nature of radiation required. Now let us come to option D. Okay, let us come to option D. If volume and temperature are such that for both gases A and B, the average interparticle spacing in each direction is equal to the thermal de Broglie wavelength of respective atoms, lambda A and lambda B, then capital NB is equal to 8 times capital Na. So here capital N basically corresponds to number of atoms. Okay, number of atoms. Okay, now to solve this particular question, we need to know a relation for the average interparticle spacing. Okay, average interparticle spacing. Now, did we see a word uniformly distributed anywhere? Yes. Look, if you read the last part of the problem, both gases are uniformly distributed in boxes. Okay, what is uniformly distributed? What is uniformly distributed? Uniformly distributed basically means, okay, uniformly distributed means, okay, each atom is like vertex of a cube. Okay, each atom is like vertex of a cube. So it is equidistant and it is surrounded by how many atoms? Can you tell me? It is surrounded by 8 atoms. 1, 2, okay, sorry, not 8. 1, 2, 3, 4, then 5 and then 6. Okay, so if you consider that atom as the origin, then one along positive x, one along negative x, one along positive y, one along negative y, one along positive z and one along negative z. Okay, so it is surrounded by 6 equally spaced atoms. Raise your hands if you understand this. Okay, now if we are set, okay, if we want to find out the average intermolecular distance, okay, average interparticle spacing, what we can do, and it is uniform now, it is uniform. So we can assume this, or we can get this, I should say not assume, we can get this particular relation. Cube root of V by N is equal to constant. Okay, so basically if I consider a 3D model, if I consider a 3D model and if I look at the top view, okay, suppose this is the cube root of V, that's side of the cube. Okay, suppose this is cube root of V, that's the side of the cube. And how many atoms am I expecting in that particular row? Okay, how many atoms am I expecting in that particular row? Look, total number of atoms is n. Okay, total number of atoms is n and it's uniformly distributed. Okay, it's uniformly distributed, right? So can I say that the length of the cube is directly proportional to, okay, length of the cube is directly proportional to cube root of n, because there are n atoms overall. Okay, there are n atoms overall which are uniformly distributed in volume V. So in V there are n atoms. So therefore in one length or on one side there will be cube root of n atoms. Have you understood that or no? You have. You have. And there is no question of radius of atoms or molecules, because in kinetic theory of gases we anyways assume them to be point masses, right? We anyways assume them to be point masses. Now if you get that, then you will arrive at a relationship that uh, cube root of n, okay, upon L is equal to constant. Okay, cube root of n upon L is equal to constant. Now if you cube that, Okay, if you cube that, then what will you get? Rather, if you just leave it as it is, then you can use that cube root of v as well. Okay, so cube root of this is constant. Okay, now what are they saying? They're saying average interparticle spacing in each direction is equal to the thermal de Broglie wavelength. Thermal de Broglie wavelength. Okay, which means now look, this is average intermolecular spacing, so that has length dimension. So although we have written cube root of n upon v is equal to constant, okay, this doesn't have length dimension. This has L raised to minus 1. So wave number dimension. Okay, so we need to take the reciprocal of this. We need to take the reciprocal of this. Sorry, cube root of v by n equal to constant, and now that has length dimension, and that is equal to what? That is equal to thermal de Broglie wavelength. So that is equal to lambda. Okay, that is equal to lambda. So what will we now have? We will now have lambda cubed into capital N equal to v, that is constant. Right? That's what they're saying. Because v is constant, because this v is the volume of the box, and both the boxes have the same volume in which gases A and B have been kept. Okay? Okay. Now, did we not find in option C, that lambda A by lambda B is equal to 2? Yes, we did find that. Right? We did find that. So can we make use of that? Can we make use of that? The answer is yes. Okay. I can say lambda A cube upon lambda B cube is equal to NB upon NA, because lambda cube into N is equal to constant. Now what is lambda A cube upon lambda B cube? That is 8. Okay, from option C. Therefore NB is equal to 8 NA. Is it right? NB is equal to 8. Yes, it is right. So D is right. Okay, so D is right. Okay, understood? Okay, which means thermal de Broglie wavelength, that formula is so far been used only in option C. Then in option B and D we just carried it forward. Now let us come to option A. Okay, now let us come to option A and see if we can decide whether it is right or wrong. Of course, we have to decide that. There's no other way out. Okay, option A. If a photon has wavelength equal to thermal de Broglie wavelength of atoms of gas A, if a photon has wavelength equal to thermal de Broglie wavelength of atoms of gas A, then the ratio of photon momentum and average momentum of atoms in gas A, that is P photon by PA, is 2 by 3. Now, can anyone tell me the formula for momentum of photon? Tell me. Yeah, what is the formula for momentum of photon? Look, we can still use lambda equal to h by p. Get p here, so that will be h upon lambda. Okay, that will be equal to h upon lambda. So we can use the same formula basically, which we use for well, any atom or any particle. Okay, but please make sure that this is wavelength. Okay, and wavelength comes first and then momentum comes. Okay, that's for, so that's for radiation. Okay, it's usually wavelength, frequency and that part, and then we bring in the momentum. Okay. Okay. So they're saying if a photon has wavelength equal to thermal de Broglie wavelength, okay, so lambda photon is equal to lambda thermal of gas A. Now what is the thermal wavelength? Have we calculated that somewhere? Have we calculated that? Yes, here it is. Okay, here it is. Or rather, let's use it this one. Oh, sorry. Now look, they are saying lambda photon is equal to lambda thermal. Okay. Now because lambda photon is equal to lambda thermal, okay, and because h is Planck's constant, can I not say that P photon should also be equal to P thermal or P of atom A? Which P? This is not pressure, this is momentum. Why? Because lambda is equal to h by P, where h is a constant. So lambda P is a constant. And if lambda photon and lambda thermal are same, lambda photon and lambda thermal are same, that is lambda, then P must be same. So P photon must be equal to P of A. Is it right? What is option telling us? P photon upon Pi is 2 by 3. That's not right. Right? That is not right because momenta are equal. So A is not right. Okay. Option A is not right. So which options are right? B not right, C right, and I think we have also got D right. We have also got D right. Yes. We have also got D right. Have you understood the question or shall I explain it again? Please tell me. Got it? Okay. Now I want to add one thing. Okay, I want to add one thing. If you go to the Wikipedia page of thermal de Broglie wavelength, okay, if you go for the thermal de Broglie wavelength Wikipedia page, okay, so in this on this page, if you read the first few lines, okay, and there you will actually find that formula that we used in one of the options. Look, in physics, the thermal de Broglie wavelength lambda Th, sometimes also denoted by capital lambda, is roughly the average de Broglie wavelength of particles in an ideal gas at a specified temperature. We can take the average interparticle spacing in the gas to be approximately V by n raised to 1 upon 3, where V is the volume and n is the number of particles. Okay, so that's the formula that they wanted you to use, and now you can't say that it's out of syllabus. Maybe you can say that it's not in the textbook, but who knows, right? And it's this is in 2020, 4 years ago, right? So it's better if you keep a track of what could possibly these newly introduced phrases mean, like uniformly distributed, right? Uniformly distributed. Okay, maybe we can say that if look, we have considered linear mass distribution, linear charge distribution, and all that stuff, haven't we? We have considered that. So when I say it's uniformly distributed over a line, what do we say? Right? We can say that the total charge, or in this case the total number of molecules, okay, upon V equal to constant, right? We can say that is the average molecular density, and if that is constant, its cube root will also be a constant. But that formula doesn't have the dimension of length. It's reciprocal of length because volume is in the denominator. So we have to take V by n raised to 1 upon 3. Got it? That's literally the same term. Average intermolecular spacing. Where is it? Yeah, this one, average interparticle spacing here and average interparticle spacing. It's the same. Okay. All right. So a different, I would say, context for the term uniform distribution. Okay.